talked yesterday, you can't have negative, can't take the log of negative numbers. That yesterday. And we also talked about the bases needing to be positive, something other than 1. So this property that we said the first, the second, and the fourth properties we're probably most familiar with. But this third and this fifth property are maybe new. I don't know. This is a good one, this fifth property. And what it is it kind of, well, it does. It uses the definition of an inverse. Remember that an inverse and its original function, they undo each other. That's what they're working. They're undoing one another. And so if I have an exponential function that happens to have a power that is a log, then you've got an exponent, the power of a log, and they are then removing one another, and I end up with just this value of x, or whatever this is, in the log power. And I'll show you how that also works with regards to, let's just change it from exponential form to log form, and how you can see we can get an x from this. In fact, why don't we do that? So remember that when you're in exponential form, generically we'll just call it b to the x equal a right now, where there's my a, and my x is this log base b of x. That when you're in log form from this, you would get log base b of a is equal to x. Right? Changing from log form to exponential or going back the other way. That's the thing you're going to have. So if I just did that with this problem, recognizing that my a is x and that my b, or my x, excuse me, is this log base b of x, then what I get is I have log base b of x is equal to log base b of x. And so those are the same thing, so x would equal itself, so you just get that. So be looking out for that property. For anything with a base and then the power that is a logarithm or a natural logarithm, I can do this. That's a good one. Property number 5. All right, so simplifying, so we're going to rewrite. Sometimes we rewrite in single logarithms, and other times we write from a single logarithm to multi-logarithm. And then we'll also, in this section, be solving logarithms. Now, understand that all these properties apply not only to common log, but also to natural logs as well. So it doesn't change. Because remember, natural log is just the log base e. What's that? Oh, oh, you know the answer for a already? Yeah. Wait, what is it?
Log a, or log base 10.
What's that answer? All right, let's do it. So when you have a coefficient in front of a log term, that is a power. It also, graphically speaking, stretches my graph. In this case, I'm shrinking my graph vertically by a third. So I have a third that is going to become a power on this 64. And I have this 2 that's going to become a power on this 5. And I rewrite this as log. Now these are all base 10s. So log base 10, 64 to the 1/3 power. Plus log base 10, 5 squared power. And then the cube root of 64 is 4. And log 25. And now I have my product property. 2 logarithms with the same base that add together means that you can write it as a single logarithm of the product. So I get log 100. Now, sometimes we're going to be able to stop here. Like if that was log of 91, I'm just going to stop. Because this probably would be a no calculator type of question. However, we can't stop on this one because we know that this goes further. We can actually go and come up with the answer for this. Remember what this means. Yes, good. The answer is 2. So remember what this means right now. It means that log base 10 of 100 is equal to some value. Well, we know 10 to the second would make this happen. And so we would want to simplify this to 2. So take it all the way out if you can to a value. Otherwise, leave it as a single log. All right, here we have an exponential. And there's another way. We talked yesterday about natural logs. Sometimes it's easier. People think of them as a log e. So I'm going to rewrite this. Log base e 1/2 x. That's the same thing as e to the natural log. So here's that one where I've got a base, that's an e, and within the power I've got also a base that's e, so when they're matching, this is the one where I can think about just taking the value of the log, in this case the 1/2 x. So with property number 5 that we just saw a little while ago, this answer is 1/2 x. If I don't remember property 5, here's what you can do. We just did this a little while ago. We can take the base, write it as log base e of some value is equal to log base e of 1/2 x, right? Changing it out of exponential form into logarithm form. And then now I can recognize that, since they're the same bases, that value must equal this value, which means I just get 1/2 x. So you don't have to memorize property 5. Just use your conversion. And you're good. Yeah. How are we doing so far? I know this is a lot of reading. So we're going to kind of blaze through it. If you get lost in something, let me know. All right. Good question was asked last period about this problem in terms of like the order that you would do this problem. Do you think we need to follow a certain order? Yeah. We have to follow the order of operations, which means I go left to right on the problem. I'm going to go and I'm going to think about doing those 2 first because they are the first difference problem that I come up with. We'll get an answer there as a single logarithm. Then we're going to subtract again, which means I'm going to end up with a product or a quotient one more time. So this first time, this becomes a quotient for log base 10 again, 3 over 6 minus log 5. We can reduce that to log 1/2 minus log 5. So now you're ready to go one more time with the quotient property and make this become a single logarithm of this. Okay. What does that equal? -1. Okay, you're going further. So Brooke says 1/10. Very good. 1/2 divided by 5 is the same thing as, say, change and flip it. So keep the 1/2, change the multiplication, and flip the 5 to 1 over 5. And then this becomes log of 1/10. But we can solve that without a calculator because we know that means 10 to some power is equal to 1 over 10. And we know that 1 over 10 can be written as a negative exponent. And therefore, what we are looking for is that this answer is equal to -1. So make sure that if it is reducible all the way down to an integer or a whole number, that we're going to go all that way. Okay?
I remember the last semester in health.
Do tell.
Where you do the 3 over 6 and you multiply the 6 and then 5 over 5.
The 3 over 6. Okay. Times 5. Yeah, that would work. Yep. say times 5 on the bottom, you just mean put the 5 down here with the 6.
Yeah.
Yes, it's the same thing. But that is essentially what we're doing, yeah. She's just saying, if you had this and you divided by 5, what you're doing is you're saying 1 over 2 times 5 in the denominator. That's just taking that 5 downstairs. Yeah, it's the same thing as 1. All right, good deal. There we go. Anything on those we need to highlight? Review, preview, undo? No. How about here, writing them as terms of a logarithm now? So don't you just have m's and n's, and we're going to see what properties these apply to. Stick some log values with them and see what we've done. This isn't the fun stuff. Here's the exciting stuff. No, that's not even exciting. Oh, this is the exciting. Oh yeah, that's a challenging problem. All right. So remember, multiplication is a product. Product is equivalent to adding logarithms. Powers are equivalent to a coefficient in front of the logarithm. So oftentimes you have multiple properties going on in one property. And that's the case for these guys. So maybe you want to do it in chunks. Maybe you first want to recognize that this first one, m squared n, is a product. So if I separate it, I've got log m squared plus log n. And then now you recognize a power property, so that power is out front. And I get this.
It's just like this. You have to write log, or you have to write log first.
Yeah, you can just write log, that's fine. So there we are. It's like starting as a single logarithm and writing it as a multiple logarithm. That's what it is. All right, next one. Let's see. Let's pick on somebody. But I think we pick on. Anyone want to volunteer to be picked on? All right, Logan's going to be picked on. All right, what are we going to do here, Logan? What's the first thing we're going to do? Just start general, then go specific. We're going to subtract 2 logs. So I'm going to have a log of an m squared minus a log of an n cubed. Yes. Yes, sir, Bob. There you go. Look at that. Oh, nice. Anyone want to take a shot at C?
It'll just be before.
All right, so going generic, this is the same thing as that. And that's the same thing as that, which means log m to the 1/2 minus log n to the 1/2. Bring out those 1/2s. Can I write it any differently? Is there anything else I can do? Is that all right? Is that okay to leave it like that? Yeah, that's all right. I guess you could factor out a 1/2. Pull 1/2 out, but that's good. We can leave it right there. That's just fine. All right. I can't wait. We're getting closer. So excited. So excited. What about these guys? Writing it as a single logarithm, it's kind of like what we were just doing, right? Same type of thing. Going the other way, though. Okay, yeah, this is like I said, this is a lot of review. So, do we need to hit these A, B's, or C's? Are you guys comfortable with this stuff? We're comfortable. You're great. Anyone need a little review on these? Who's got an answer for A? See how we're doing on this. got an answer on the A. Log base 3 of 20. Log base 3 of 5 times 4. So log base 3 of 20 on that one.
Do you want us to keep it?
No, because on this one,
So it's not telling you to solve.
yeah, it's not something I can do without a calculator. So we're good stopping it there. That's fine. If it was reducible, if I kept going, like that was a log base 3 of 9, then I can say, oh, that's 2. Right, how about B? What? Natural log of 5 over 2. Yes, natural log of 25 to the 1/2 power minus natural log of 2. Natural log of 25 squared. Natural log of 5 over 2. Again, that's not something without a calculator I'm going to be able to do, so I can stop right there. All right, these are easy. How about that? Let's kill this so we can get to the exciting stuff. Got it, Harley? Hadley?
Log base B of mn over b.
Log base B, m times n over p cubed. Right? Remember that goes back to power. Subtraction tells me I've got quotient going on. So we're good there. Okay. So here's what we did in the third period. We were able to kind of handle the first one, part A, pretty easily, I think, for the most part. But then I let them chew on B and C, and I didn't give them any answers. And I had some folks staying in after lunch trying to work on this stuff. And I said, you guys aren't going to get the answers until you see the YouTube. So you get the benefit of actually seeing the answers. Thank you. But these are great. These are great. You know, I think she did. Oh, no, that's not for her. Thank you. It's for you, man. Look at that. Doctor appointment. There you go. 2:10. Which means 4 minutes ago you disappeared. All right, so here's the deal on this. Good thinking problems. In fact, I told some of the folks that were staying after, I think I would put maybe some of these on as extra credit. But I'm going to get you guys to think and chew on it at the very end. If we don't have it, I'll give you the answers and how we do it. But we're going to, real quickly, we're going to do A. We're going to skip to the next slide and then finish that up, and then we're going to come back to this. Okay? So I kind of want to give you the flavor of what we're going to do with part A, and then we'll see if we can tackle it. So what I want to do is I want to rewrite this log base 6 of 40, and I want to create it as an expression that involves x's and y's. Now, it doesn't have to involve both x and y. It could. It could have constants in there, but somehow I'm going to see if I can get this to become a relationship of x's and y's with constants. There. So how are we going to do this? Well, we recognize that x is representative of a log base 6(2). So every log base 6(2) I have, there's an x. And a y is represented by a log base 6 of 5. All right? So we're going to try and use those, log base 6(2), log base 6 5s, and we could use other things as well, to come up with a log base 6 of 4. So here's my recommendation. Start generic. Think about, how can I get a 40? What are some ways that I can get a 40? I can multiply 8 and 5, right? You can multiply 8 and 5. Now 5's good because I got a log base 6 5 there. So start out generic. How do I think of these as a factor or a quotient? So how do I get two factors that give me this 40? And one of those ways would be, all right, let's do a log base 6 of 8 plus a log base 6 of 5, right? Because remember, that's product rule right there. Product. What's that? It's 4x plus y. It's not quite 4x plus y. Close though. Close. Okay, do we all agree that this is a y? Okay, that's a y. All right, we know there's a y in this expression. So somehow we need to make this work with a either log base 6.5 or log base 6.2 or something other unique log y's that I might end up with a constant.
2 cube.
Why don't we think about a cube? That's a great idea. 8 is a cube root, or not a cube root, is a perfect cube of 2. So what we're going to do is we're going to change this. Instead of an 8, we're going to write it as a power. So log base 6 of 2 to the third. And then now, oh, there's the power property. Oh, comes out. Now we get a 3 log base 6 of 2 plus a log base 6, 5. And then now I recognize that that is an x, and this is a y. So I can write this out as 3x plus y. And that would be our equivalent expression in terms of x's and y's for log base 6. So that was the easy one. Next two were tough. So you guys got a peek at them? Log base 6 is 3, log base 6 is 15. I will tell you, once we find log base 6 of 3, it's easy to find log base 6. Okay? So we're going to come back to this just a second. We're going to skip ahead one more, and then we're going to come back. Is that all right with you guys? Okay. So let's go. We'll wrap it up here with some solving problems, and we'll come back to those challenge problems. So solving is a lot like when we do, if we had radical problems and we did our isolation, right? We want to get all the radicals isolated by themselves so that we can undo them by taking the power. I'm trying to get everything on the same side of the equal sign. The reason we want to do that with logarithms, although I don't necessarily need to get all of them on the same side. I want to get one on one side and one on the other. I could do that if they have the same things. But I'm going to think about using properties. I want to take this and I want to write it as a single logarithm. I don't want to solve these things until I have a single logarithm. So I can't do anything with this until I make log base 2 of x and log base 2 of x minus 2 a single log base 2 value. So what property do I have going on? Product. I've got a product property, which means I can then write this as a single log base 2 of an x times an x minus 2. And then this would equal 3. Then we have a little work to do simplifying there. So we have log base 2 distribute the x squared minus 2x is now equal to 3. Maybe you put parentheses around that, because that's what you're taking that's your log, right? Log base 2 of that value. And then this is where I want to be. I have a single logarithm. I'm ready to solve it. This again could be a no calculator problem because all I need to do here is switch the form. I want to take it over to exponential, which makes it become what? 2 to the third equals x squared minus 2x. And now this just becomes a quadratic. So I get 8 equals x squared minus 2x, 0, x squared minus 2x, minus 8. I get x minus 4 and x plus 2. Now, these problems potentially produce extraneous solutions. So that's what I could be, but I want to make sure I go check them. And when we check these, we always check them into the original problem. So I'll be plugging them into this. Now you don't physically have to put the values in and calculate them out. So what you want to look for is that if I use those values and I plug them into the original, do I ever take a log of a negative number? And if that happens, it's a no-no. You can't take logs of negative numbers, so it wouldn't work. Which means checking the negative 2, the very first one I plug it into, log base 2 of x. If that becomes log base 2 of negative 2, that doesn't work. So negative 2 is an extraneous solution. I won't use it. be good, because log base 2, 4, I get that. And then if I put 4 into the other one, 4 minus 2 is 2, which is positive. Again, I just want to care that they're positive, that's all. I don't care what the number is. I just want it to be positive. So my only solution to this one would have been that x equals. Do you remember this stuff? This isn't new. Just maybe it's been a while since you've seen it, but it's not new. All right, how about that one? What are we going to do there? We got logs on both sides. That could be okay as long as it's just one log and one log, but I can't have one log and 2 logs, or 3 logs, or 4 logs. I got some work to do here. What should we do, kids? Just combine the 2 on the right side. That's a great idea. Combine them, what do we get? Yeah. Log base 2 of x times 6. Yeah, so now we're going, and we're going to take a look at, rewind, property number 3. 2 logarithms, same base, means I can just set m equal to n. That's what we've got going on. That's what's happening right here. We have both log base 2s. So now I could subtract log base 2 6x over, get a 0 on the other side, switch it with quotient property. I can write it as a single logarithm equal to 0, and then transfer it to an exponential, something to the 0 power, and then find my x from that. That's a lot of work. If we already have it set up where these two are the same bases, then that means x squared plus 8 must equal 6x. And then here's another quadratic. So x is equal to 4 and 2. And since both of those are positive, as long as when I plug them in I don't create a negative, again, looking at the original, I won't create a negative with either of them. So those are both solutions. But sometimes they both work. Sometimes you have an extremes. All right. So that's our solving bit. And again, could happen with natural logarithms, the same thing, same properties apply. So, you guys ready for the challenge? Yep. Ready? We got slightly less than 10 minutes. Here we go. Here's the challenge. B. That problem is the one we need. Once I get B, I can answer C. I didn't give third period a whole lot of direction on this. I just let them kind of go at it. I think I'll just kind of do the same with you. I'll just let you go at it. See how you can. I'll have to give you the answer when we get down to like the last minute or so. Unless you can pair up with somebody, I don't care. See if you guys can tackle this. How do I get a log base 6(3) somehow related to an expression that has x's or y's and constants or whatever? All right, there you go. There's your task at hand. Here it is. The trick. I said let's think generically about this. So how can I produce it? I can produce it as a quotient of 6 over 2. Okay? That then can be written as a difference. As log base 6 of 6 minus log base 6 of 2. So we see that there's an x in the problem. This part here, what is this equal to? That's equal to 1.
It's just like log base 6.
Yeah, it's anytime I have a log of a base and I'm taking that value,
Could it be log of 6 minus 6?
it's just 1 minus x.
This is 30. This is 30.
So, don't overthink them. Start out with basic stuff and see where you get. So now that you know that, I bet you can easily get this answer. What's that going to have to be? Y plus 1 minus x? I think that's right. I think you're right. Because log base 15 can come from a log base 5 times a log base 3, right? We already know what log base 3 is. It's 1 minus x. So we took this and we made it a product now. We had that. We just found what log base 6 3 is. It's 1 minus x. We know that log base 65 is a y. So there's my answer for log base 6 and 15. Good little problem, huh? No? All right, there we are.